Hello fellow problem solvers, so today we're going to be doing a problem from the 2021 IMO, problem number 3. I suggest you try this problem out for a minimum of half an hour and try to get as many points as possible as though you were on the IMO and you try the last geometry problem for half an hour at least. Ideally you try it for 2 hours to 2.5 hours, but you don't want to do more than 4.5 hours. If on the other hand you'd like to go along with us, I suggest you draw the diagram and put your first ideas out on paper for the next 20 minutes. So now, let's begin. So with this problem, I want to point out something that's very important in geometries that are long. And it's a principle that I've mentioned before in my videos, and that is that when you have a lot of things, so we have what, AB is greater than AC. When you have a long problem in geometry, you want to draw the points one at a time. So D is somewhere here on the angle bisector. And now we have points E and E. And then we get a point X, O1, O2. But the thing is, okay, let's first try to see what do we get when we put point E. So point E says ADE is DCB. So that's a point like this. Now we have this is E. Okay, now this immediately tells me once I do this, I say AD intersection BC is point S, then I'll get that ED is really the tangent to the circle around CDS. Okay, interesting. Now before I do anything else, let me try to just calculate the angles. And these are different things, like this EDB are not collinear. So if this is X, this is gamma minus X, then this is X. I think I get all the angles. This is beta plus alpha half, which makes this angle CDB, this makes it gamma plus alpha half minus X. And this is alpha half plus X, which makes this angle beta plus alpha half. Yes, because the X's cancel out, and we have beta plus alpha half. Okay, so now these are some of the angles that we have. Okay, can we do anything about this? I invite you to take 5 to 10 minutes and see if there's anything more that you notice just by adding the point E. And for me, I want to explore this tangency condition. So let me take the other intersection with CDS and AC. So let's call this point T, just for now. And now we have ED squared is ET times EC. And also gives us some angle condition, right? So this angle right here must be gamma minus X. Okay, so we have gamma minus X, alpha plus X, which makes this angle right here, gamma beta plus alpha half. Okay, which is also sensical because this is beta plus alpha half. Now, is there anything more that we can do with this? And the answer is truly we don't know. We would have to figure it out. But we have, okay, we have a power of point for A. Now we have AD times AS, which is something that's constant, is AT times AC. Okay, so now if we took the other intersection here, we would have, like, with BSD, if we took this intersection, like this is a tangent here, that would be point F. If we took this other intersection, called this point, say, Q, we would have AS times AD is also AQ times AB. And now we also have that FQ times FB is FD squared. Now, is this useful or not? We don't know. It seems like something decently interesting. I'm not sure about it yet. Now, I couldn't find anything with this, so let me draw another diagram and try to see if there's something else that may come up. Okay, so maybe let's look at E and F at the same time once we add the point D. And now, okay, we have this angle, we need it here, and then we have, so this is X, this is Z, beta minus Z, gamma minus X, this is Z. Now, I invite you to pause for 10 minutes and see if there's anything you can find out here with points E, F, C, D, B, and A. And for me, I was trying to figure out, because I know that at the end we need to prove that BC and EF and O1, O2, we need to prove that these all intersect. I was trying to see, like, is there anything that I can find with EF, B, and C? And I wanted to explore this thing because EDF plus CDB, this is X, this is Z, this is X, this is Z, so this plus this is 180. Now when you have two angles like this equaling to 180, the natural thing for me to do was to intersect AD again with the circumcircle. So I can get this angle that we have here on the other side. And what happens when we do that? We have Z, we have X, let's call this point T. And now what do we have? We have ADT. Okay, so we have this is Z, Z, Z. Okay, and this is alpha half. Well, now we have some similarity. So what does the similarity go? So let's see. We have that AFD is similar to, so A, again we need an A, F is the acute, so ACT. And so this gives us AF over AD is AC over AT. Before going into CT and going into FD, which seem less useful, like more complicated, I wanted to see these. And now what do we have? We have AF over AD. AF over AD is AC over AT. Okay. Now what do you notice with this? Well, for me, what I notice is that at AD and AT, I will get on the other side of it, I'll have the same similarity here, and I will get AD and AT as well. And I'll get AE over AD, just by reasoning by pure analogy, is AB over AT. And now what does this give us? Well, this gives us AF over AC is equal to AD over AT, which is equal to, so AD, AT, it gives us AE over AB. Okay, this looks interesting. Now, what does this mean? Well, it means that AB times AF is AC times AE. Oh, so now this gives us that CEFB are concyclic, which is a big deal now. And the reason it's a big deal is because it gives us these angles, it connects E and F somehow. We know that these are concyclic, and the fact these are concyclic gives us angles. It gives us this is beta, this is gamma. We have a lot more information now that we know that C, E, F, B lie on the same circle. And now, just I want to point out that this took us less than half an hour of exploring. And it's probably a point. This is almost certainly a point for this problem. So this is just to show that it's useful to sometimes spend a little bit of time on the third problem, especially if it's a geometry, to be able to fish for a point or two, which can be the difference between a bronze and a silver, a non-metal or a metal, a silver or gold. So that's why we're doing this. And now, putting this intersection, like calling this intersection S, makes a lot more sense, because now we have that these are concyclic, so we have something strong with S as well. We have SC times SF is SC times SB, which is very cool. And now here I invite you to pause for another 20 minutes and try to push the problem further. Here's my next step. So now this is what we have. We have these 4 points are concyclic. We have this intersection as S. And the other 2 points, 3 points actually, are X, that's on AC. And we have the centers of this circle and this circumcircle. And these are O1, O2. We need to prove that O1, O2 goes through S. Or in other words, if there's an intersection between these two circumcircles, and that's K, the second intersection, we need to prove that SD is equal to SK. So now with that, it makes sense for us to look and try to connect S and D somehow. And now here I invite you maybe to pause for 5 minutes and see if there's any way you would think to try to connect them. And for me to think I would try to take the second intersection of these circumcircles, because then I have, by the radical axis theorem, if that other point is, say, P, then I'll have that SD and P are collinear. And now what holds for that point P? Say it's here. Well, we have that this angle, the angle DPF, is equal to what? 180 minus this. So this is beta plus alpha half plus X. And then the angle, we have DPB is equal to 180 minus X, which makes the angle FPB equal to 360 minus all of this. This plus this is, okay, so we're left with gamma plus alpha half. And now if you stop for a second, you'll notice, wait, FPB needs to be gamma plus alpha half, but we already have that FD B is equal to gamma plus alpha half. And this is inside this. And now it takes just a second or two to realize that means both of these angles are 0, i.e. that D and P are the same point. And a very clean way to prove this now is to say, let's take the angle bisector, not the angle bisector, the tangent of CDB at point D. And now this forms the angle Z here with the, take a point here, that's P prime. Now we have P prime DC is equal to Z, which implies that the angle P prime DE is equal to beta plus alpha half minus Z, which is equal to the angle DFE, which implies that P prime D is tangent to the circumcircle around DEF as well. So this implies that the tangent of these two circumcircles goes through S, which implies that SD squared is SC times SB is SE times SF. And now writing this would give you the second point in all likelihood for this IMO problem. And now that we've explored this far, which is really, if you spend an hour with this problem and try to really do it step by step, you just need this idea, and then everything else follows almost naturally, like when you just calculate the angles. I mean, the only sort of intuition you need is the intuition to stay with a diagram and try to get more out of the problem here. And now with this, I invite you to pause for another, let's say 20 to 30 minutes and try to push the problem further. See what your next ideas are. And if you do this, if you're going to introduce this point, just name it K so it's easier for you to follow along. So now here's the next step. So now we look at the full picture and let's see what this K is, we take the other intersection because O1 and O2, the easiest way to sort of prove this, the most intuitive right now, is to take these intersections of the circumcircles around DEX and ACD, let that be K, and what we need to prove is that SK is equal to SD. And now what we're going to be doing is trying to we can explore, push the problem further, or we can look at it backwards, sort of look at what it is we need to prove and look at it as what do we have with this intersection. Like we need to prove that SK is SD. This is looking at it backwards. And there are a couple of things that can give us, and depending on a different perspective, we can do a different thing. But now, do we have any angles with this point K? We have that the angle DKX is equal to the angle DEX, which we already have. That's equal to gamma minus X plus this angle right here. So it's like angle EDC plus gamma minus X. And on the other hand, we have that the angle DKA is equal to the angle DCA, which is equal to what? It's equal to gamma minus X. So the angle AKX is equal to the angle DEC. And now with this, what is this angle? Well, this angle is beta plus alpha half. And now my question for you is to take maybe a minute or 5 minutes and try to figure out is there anywhere else where this angle beta plus alpha half shows up. This is of course just one perspective, and here the perspective is beta plus alpha half. If you intersect, like look at this perpendicular bisector, and if you intersect it with a circumcircle at a point, say call this point M, and now what do you have? You have that, and call the other point of intersection with the circumcircle N. If this is alpha half plus beta, so this is alpha half plus beta, which makes these 4 points concyclic. And now we have something extra that holds for K. Maybe it's easier to look at K as the intersection of AMX and ADC. Like, actually right now what we can do is we can actually just forget about the points E and F. Like we have a new way to look at what K is. And now I would invite you to take another maybe 10 to 20 minutes and be the judge. Is this a valid sort of thing? Is this a thing that's interesting? Is there a different perspective shift that can maybe give us a simpler problem here? And I would be the judge to actually try out this a bit, because what do we have? We have a new definition of K. K is the circumcircle of AMX intersection of the circumcircle ADC, the other actually not, actually yes, AMX and ADC, that's what K is. And now what we're looking to prove, like we can still have S is just a point such that SD squared is SC times SB. That is enough and sufficient, and now we are without E and F. So given there are a lot of new circles, let's draw a different diagram for this. And now this is what we have. We have X, we have AM, and we pick a variable point D, and what we do with it is just intersect ADC and this other circumcircle, and name this point K. To prove that SD is equal to SK, we actually don't need S. And the reason why is this. This is, again, if you have more theory, it helps with geometry. Geometry is the thing that really, the more you know, the easier the problems get. And here that thing is, if you take you have a triangle, and you have this, where the tangent intersects with a triangle, say x, y, z, the tangent from x to the circumcircle of x, y, z intersects y, z at the point T. Now, the set of points with center T and diameter Tx will lie on the same circle, and a thing holds for them. If you take any point that's on this circle, take this point L, such that TL is Tx, then what you can prove is that Ly over Lz is xy over xz. And this is just through similarity, like this over this, you get over these two similar triangles. So you get the same thing holds for every one of them, but you can also prove the converse. If this over this, if Ly over Lz is xy over xz, then you also have that TL is Tx. So now here, we don't really need S just now. If you want to look at the cleanest picture possible, we just have this K, and we need to prove that KC over KB is equal to DC over DB. If we prove this, we are done with the problem. And there are other interesting things about Appolonious circles, which these are called, that you can look at this as really, on one hand, this is DC over DB, is KC over KB. That means that K would be on the Appolonious circle of the triangle DCB. But you can also look at it as, say, B is on this Appolonious, on the, say, what is it going to be? I think it's the C Appolonious circle of the triangle KDC. You can also look at it as that. And then what you need to prove is that if KD intersects MN at a point, say, called this Z, then what you need to prove is that ZC is tangent to the circumcircle around CDK, which is the same circumcircle around CDAK. So that's the whole circumcircle. And now we can look at maybe proving that. And if that's not too hard for you, I invite you actually to pause for another 10-20 minutes and see if this is something that you would like to try to prove. Here's the next step. So before I tell you the solution, I want to tell you what it is I actually tried. I tried a trigonometric attempt, and what I needed to prove was, using the lemma that if sine of x over sine of alpha minus x is equal to sine of y over sine of alpha minus y, if both x and y are between 0 and alpha, that implies x equals y. And I tried to use that to prove that the angle ZCD over ZCN is equal to sine of x over cosine of x plus y, because I know this is 90 minus y. Of course, first name these x, y, z, alpha, just have everything on the table. And then I saw what this sine over this sine actually is, and it's something along these lines. And then in trying to figure out a nice way, like I would thought of, well, I can use the sides of some sides here to like get some of these values. For example, sine of x plus y plus z plus alpha. Where do I have x plus y plus z plus alpha? Well, I have 180 minus that in KAC. So I'll have KC over, say, I have alpha over KA. So this is what I'll have. This is going to be equal to KC over KA. And now I have sine z and cosine of x. Cosine of x is what? We have that it is CM over this. And now what am I looking for? Z. Where is z? It's AM. So I'm looking at AM CM. So sine z over cosine x is AM over CM. And now look at this. This is actually this is like KC over cm am over ka. And I was looking at this. And then I got stuck. I was also looking at ways to use this fact, like find cosine of x plus y somehow and put it all, just like have it all depend on the sides of the triangle. And then I saw, wait a second, there are a lot of circles going through A, and this is variable, like K and D are dependent on each other. So I applied an inversion with center A and some radius. And then I got a nicer diagram. I got some lines instead of some circles. And then on top of that, I applied an inversion on C to get an interesting problem, which I'll just like show you right now, which is where you have these angles at 90 for x, a, and m. You have C as the intersection of these. And then the way you get D and K is actually quite nice. You get it as one is on one circle and the other one is C. That point intersect the other circle, like one is on the circle CMX, the other one is on CAN, and you have their intersections, like you have like these three, D, C, and K lie on a line, and then Z is the intersection of the circumcircle of KDA and this circumcircle around MXAN. And you need to prove that AZ is parallel to Kn, which is a very interesting problem statement that seems simpler. And I worked on this second attempt for an hour, probably half an hour at least, maybe even an hour. I forgot, then I lost track of time. And that failed and this failed. And now as I was making this video trying to explain this trig attempt, I was looking at, wait a second, how would I get x plus y? And I thought, wait, I can maybe have x plus y here. And then I realized, wait a second, I invite you here to pause for 5 to 10 minutes and figure out if there's something here. And the answer is, if you take this intersection, CQ intersects MN, if this is point, say, call it Y, then what do we have? What we need is that this angle, ZCY, we need this to be X. If this is X, looking at the problem backwards, very useful in geometry, we will have that this ZC is a tangent to the circumcircle around CYM. So we'll have CZY times ZM is equal to ZC squared. But also we need ZC to be the tangent to this. So what we'll have, looking at it backwards, is ZQ times ZK is ZC squared again. So if the problem statement holds, then these four lie on the same circle. And it's easy to see they do because this angle, MKZ, is x plus y. And so is this angle. Like this is why I took this intersection. So now we know for a fact, we know that ZY times ZM is equal to ZQ times ZK. So we know these 4 points are concyclic. So now what's the only thing you need to do to finish the problem now that you have these four are concyclic? You will have that ZC is a tangent to both the circumcircle around, let's write it down, KADC, and you would have it's also tangent to the circumcircle of CYM. So we have CYM, and we also have that now KMYD are concyclic. So what do you get from the radical axis theorem here? Because like when you have circumcircles like this, use the radical axis theorem. And what you get is that, well, the radical axis of KADC and KMDY is equal to what? KD of, say, KMYD and CYM. Well, that's equal to MY. And now we have the radical axis of KADC, so this circumcircle, and CYM. Well, we need that to be CZ. We have all, like it is CZ actually, by the radical axis theorem. And now what's enough for us to do is to prove that these two circles are tangent to each other. And that's pretty simple to prove. And the reason why is just like draw a tangent, say with the angle x, and you will get that if this is a tangent, intersect, say at this point t, actually wait, do I have t? I might have had t before, let's call this point O, I haven't used that. Then OCQ is OCY, and you'll have OCY is x. So OCY is x, which is equal to YMC, so it's tangent to this one. And OCD is also x, which is equal to CKD, which solves the problem. So now we know that these were radical, like due to the radical axis theorem, all these intersect at Z, which means that ZC, due to the fact that these two are tangent to each other, is the tangent. And now this solves our problem. So now with this, I invite you to pause for another 5 to 20 minutes and try to write up a solution. That's what we'll do now. So the first thing we do is we say EFBC is concyclic, and the way we prove this is intersecting AD with the circumcircle of BCD, again at T, and then using our similarity, and then after this we prove the second claim, which is, so we have this proof, we calculate CDE as ABC plus DAB, and we then calculate also the angle EFD, because we need that, and then we just take one of the tangents to one of the circumcircles, and we get that from the relationship, from the angle relationship there, that it must follow that SD is tangent to the other circumcircle as well. And now with this, we move on to our third claim, namely, and the way we do now the next claim, we take S, we let K be the second intersection, we let AD intersect ABC at N, and XN intersect ABC at M. And now what we have with that, we prove that K, X, M, A are concyclic. And the way we do this is just by angle chasing, and we have that AKX plus AMX is 180, which proves that these 4 points are concyclic. And with this, we move on to the fourth claim, which is, we say let DC and MN be equal to Y, then we prove that Y, D, K, M are concyclic. And notice that in our proof, if you just read it without any of the context that I gave you beforehand, you would be thinking, why is this person proving this? Well, we prove this. We have two cases. These in the angle ACM, and it's outside of the angle ACM. These are the two cases. And in both cases, YDKM are concyclic. And now we move on to the fifth point, which is, and we get that CMY and ADCK are tangent. That's our fifth claim. And we prove it again if M is in ACD or if D is in ACM. We have two separate things that both give us that ZC is tangent to the circumcircle around CADK. If it's tangent to CMY, then it's tangent to CADK. And now we move on to the sixth claim, which is sort of starting to bring it all together, which is, and now we start proving our final claim. We said if ZC is the common tangent of CMY and ADCK, then we have by the radical axis theorem that CZ, MY, and KD are concurrent, i.e. that ZKD are collinear. And now from ZC tangent to ADCK, we have this thing, because ZC is ZB, because Z is on MN, we have that ZB is tangent to BDK, which gives us that DB over KB is DC over KC. And now with this, we move on to our seventh thing, which is, and the way we do this is by proving really the converse of the Appolonious theorem. And so what you do is you take H and I such that these are where the internal and external angle bisector of BCD meet the sides BC. And then you do some calculations and you figure out that that implies SD is SH is SI. And now from the angle bisector theorem, both the internal one and the external one, what you get is that DC over DB is HC over HB is IC over IB. And now using the star thing we figured out before, which is this thing right here, that implies that KC over KB is HC over HB is IC over IB. And now this implies that IKHD all are in the same circle, because it implies that IKH is 90, which implies these four lie on the same circle. And because we already have that SD's, SI's, SH, that implies S is the center, and now that implies that SK is equal to SD. And now with this final claim, we finish the problem on the next page, namely, and the way we finish it off is from SD is SK, we have S is on the side bisector of DK, then we get O1 is on the side bisector of DK, and O2 is on the side bisector of DK. all of which implies that these 3 points, O1, O2, and S, are collinear. And given S was EF intersects BC, this implies that EF, BC, O1, O2 are concurrent. And now this solves our problem. We can write down QED. And as always, thanks for problem solving.